First, let me thank you all for the award. It goes back a long ways in my history, and even though I started in the 60s, forming of Acadia was at a transition point. The gap between 1981 and 1986, I did a startup. We would have called it a BIM company at that point in time, but BIM hadn't been invented as a term. We used a language called Modular 2 and were venture capital backed, and the company was sold to Lockheed in 1987. Yeah, so I gave it a run at that time. At that time, actually, computer-aided design and architecture was really driven by Autodesk, 2D drafting, and intellectually it was a lousy time to try and start things. The venture capital people finally realized it was going to take as much training and education of the architectural community to sell one system. They said it wasn't going to work well, and that kind of ended the company. I have a voice? I should just bend it over. Okay. Yeah, I'm sorry, my voice is a little weak. I thought I would start off by starting from the 1975 or so and move forward. I want to just mention the people that influenced me a lot. I was a TA for Chris Alexander at Berkeley for 2 years. With Horace Riddle was also there in planning and was a strong influence. I went to Carnegie Mellon in the late 1960s with Herb Simon and Alan Newell being the people who really brought me to Carnegie Mellon. Of course, Alan Newell was a Turing Award winner, top award in computer science, and Herb Simon was a Nobel Prize winner, first Nobel Prize winner in a social science. And I think Simon's book, The Science of Design, or excuse me, The Sciences of the Artificial, are still in publication. I had gone through 8 editions last I heard. If somebody's interested in the history of computation and design from an AI perspective, if you look at the different editions of his book, each one's modified from the previous one and tells his change of thinking. I go back and start at the beginning of computer-aided design. Of course, the issues were hardware, software, and people, and the hardware ones were really the constraining ones for a long period of time. So the image on the left, if you haven't seen that before, that's Ivan Sutherland working on the Whirlwind, the campus computer at MIT. They took the whole computer system down at the university to run his PhD thesis. And the second slide is from Art Bale, who was, as a young man, who ran computation and had really the first commercial semi-BIM tool, 2.5D, at the University of Edinburgh for the Scottish Housing Council. And Tektronix storage tube displays, how many people use those as their first CAD systems, because they were only $4,500. That was a very cheap machine in those days. The one on the right, I think, is a Summa Graphics. So I want to talk a little bit about the development of computer-aided design, because and some of this is related to the work, the presentation that I made last year, that identifying what was the shape, what was the solid, what are the operations on those on those data models was a huge challenge. It was not just a challenge for us, it was a challenge for mechanical engineering, for aerospace engineering, the movie industry, everybody which was dealing with 3D objects. And there were conferences like quarterly, at different parts of the U.S. and also the world dealing with these issues. The Boolean operations by Ian Braid in 1973 was a huge, exciting transformation of the industry, that I could subtract one shape from another, add two shapes together, doing the union with some reliability, which wasn't perfect for 5 years or so. That really gave us the tool base. I think Carnegie Mellon had, my lab actually had the first solid modeler running in North America by just a few weeks, actually. It was really a horse race. So on the outside, the Boolean operations look very simple. It's a face-face intersection operation, and coloring the faces inside and outside, putting all the outside faces together for a union, all the inside faces together for the intersection. You can get a fairly reliable version running in a semester. Now we used to do that at Georgia Tech for a while. And then you could build up assemblies of Boolean operated shapes. One of the things that I take credit for, and the speakers today talked about topological operations. One of the huge challenges if you're doing shape modeling is how every operation you do, you change the topology of the system. The topology of face edges, how things are connected together, what's adjacent to what else is dynamically changed. And then you apply the geometry to the vertices and lines and surfaces, and that just gives it some proportion and dimensions. So a hexahedron is a hexahedron regardless of whether it's a brick or a block of apartments in a city. And the Euler operations provide the computational manipulation of the data structure so you can turn any one topology into another topology. And they're embedded in, I have up at the top. If you look in the ACES or Parasolidus libraries, which are the libraries used by almost all the CAD/CAM systems today, they incorporate the Euler operators as their internal data structures for manipulating shape topologies, whether that's 20,000 faces or 4. And so we publicized the Euler operators and implemented the early version of them, and they're embedded in all your software. You don't even know it. You're probably running 1,000 or so Boolean operations in semi-real time at this point in time. To me, it's amazing. I know I worked with GE back in the 1980s. They were trying to put the Boolean operations on a chip. They spent a lot of money doing that and it still took like 20 seconds to do the Boolean operation. Not on rectangular solids, but more complicated ones. So the evolution of computation included hardware and software and systems, and just to pick out a few points, that Sutherland's thesis was in 1963 on a Whirlwind computer on campus. That's at MIT. The solid modeling operations by Ian Braid was a game changer for everybody. Everybody could get the Boolean operations running, but getting them debugged was a huge challenge. Even a 64-bit real-time arithmetic, it was hard to get consistency on if I have two lines crossing each other at 6 decimal places or 12 decimal places, where they crossed, where the intersections were. Those round-off errors were very serious for a long time. Ian Braid made a proposal to all the CAD companies. He said, instead of everybody working on their own systems trying to debug them, invest in my company, shape data, it was called. It was in Denver, Colorado initially. And I will build you a debug version of the Boolean operations and a geometric modeling library, $100,000 a package. They sold a lot of those. And in the middle 1980s, solid modeling became, IronCAD, Intergraph, SolidWorks. A lot of packages were developed at that time frame because they could buy that library, start a business, and get in production, have production systems in a year or so's time. Parametric technologies came along fairly naturally. After I built a shape, I still had to dimension it. Those dimensions initially were just annotations. Then they realized, well, those are parameters. I can use those to control the dimensions of things. So it was a smooth evolution. Parametric technology came out in the middle 1980s, and that changed the other industries too. In the same time, there were a number of interesting CAD developments in the AEC area. In 3D, there was a basic decision that was done by many organizations. Am I going to model the product, in this case the products of building, or am I going to model the representation? That is a drafting system. We're going to represent the operations on a drafting system. And while manufacturing and aerospace took the model of the product as the base decisions moved in that direction because they had lots of uses for it, especially in the manufacturing side, the AEC area took, let's model the representation. And of course we got 15 years of AutoCAD as a result. There were a lot of other companies at the same time doing that kind, but there were a few 3D systems also. I had a system called Glide that was fairly widely published in different magazines and TV shows at the time. And the Army Corps of Engineers supported the work, along with Harold Borken's work on the later stages. The building models had certainly the B-rep geometry was the main representation, had extrusions also, and then started exploring object types, but they weren't hard-coded into the system. They were programmable. I had the Euler operators to build the topologies, assign the geometry to it. That was all available to the user, how to build those. So we could try out lots of different parametric modeling strategies. And that's about where we were when we were proceeding, and I started that company. In the meantime, there was a number of applications that came out that weren't object type. They were generic types, generic geometry. They were easy to use. Form-Z by Chris Yesios was a very popular system, still is. He was here yesterday at the conference. And he's still got a large base of users. Doug Stoker led a team at the SOM called, the system was called AES. It was supported also by IBM. And that came out in the middle 80s. Had 3D modeling, had relational database backend, multiple building systems, kind of simplified input-output, and introduced some analysis application. I think they had a structural analysis interface. That would be considered a pretty good system today. But in the 1990 time frame, there was a huge recession in the real estate industry, and SOM said, we're really not in the computation business. We're going to stop support for it. Very, very sad story. Richard Meyer, by the way, was using AES for the Getty Museum designs in LA as that was being built. So that was exciting system. There were other systems. I mentioned Borkin system. RUCAPS was a British system that existed for quite a long time. It turned into the Sonata system down below. GDS came out of applied research at Cambridge. A guy named Paul Richens, who's now at Bath University, developed it. And most of these are commercial systems. Borkin system was used by the Atomic Energy Commission. RUCAPS was done by a number of projects. The point here of listing these is that there were products, there was a market, but that market was small, so these systems couldn't all be supported by the marketplace at that time. And the transition to 3D modeling and understanding how to produce building designs and building information off of that was a huge learning curve. I think the universities were partly to blame at that. Certainly Carnegie Mellon and my group did a lot of work at that time trying to change that. But it was a battle. I think the other industries realize if we're going to survive, we have to do this. And the U.S. marketplace in construction is still a kind of regional orientation. Getting the land, knowing your politicians in the region, that kind of business relationship was, to some degree, still is very strong. But all of these systems had objects and assemblies. They had object modeling by topological structure. You drag walls around and you change the geometry of the spaces inside the walls, and the walls grow or shrink depending on if they're angled or not. Angled into the other walls. Editing operations on assemblies as well as individual shapes. Mapping between different views. I don't mean views like plan, section, elevation. I mean different views like structural model view and architectural model view, or fabrication level modeling views. All of these ideas were developed in the 80s with these systems under development. I didn't put our system at this point in time was called GLIDE, as the earlier slides represented. I mentioned Bo Christer Bork. I think he's now retired in Helsinki. He did the first serious work, a whole series of maybe 10 papers on building model representations for different kinds of uses. Energy analysis, CFD analysis, construction orientation, design orientation, and developed the different views. I ran in by accident to the founding papers for Acadia, and this is a copy of it. October 7th, 17th, 1981, when we had the founding meeting at Carnegie Mellon. You might recognize some of those names. I had dinner with Harold Borkin last night, Kevin Kavanaugh, Bill Cooper, me, Ulrich Fleming, recently retired. Okay, Warren Wake, John Tector, so on. And the corporation papers were approved in '84, and a statement of intent. We almost was named ACAD E, where E was IAE because there's architectural engineering demanded that they be added to the name if they're going to go ahead. So we've never had strong representation from architectural engineering as a result. So what we got instead was AutoCAD and Summa Graphics and Vectorworks and other, not very many of those systems now exist, but many of them start out as 2D systems, and there was a big competition at that time for 2D drafting systems. And even today, we don't hear much about AutoCAD being used in mechanical work. But there's a lot of offices out there that are still using AutoCAD in the mechanical piece fabrication shops. But there still were some fundamental questions. How were these CAD tools organized? Did I have a piece of geometry that I attached attributes to, which is what AutoCAD did with architectural desktop for a long time? They could build elaborate fixed algorithms that would generate a stairway or a hipped roof, whatever. Early competition to Revit, but was orders of magnitude better than Revit. Other systems had some more complex ways of managing attributes, so the attributes could be parameters for the geometry of the shape or the placement of the shape, and write equations that were in those. We had a full parser in Glide so that we could do all the math, algebraic computations. And then different levels of handling both attributes and relationships. Attributes, relationships, and geometry are really the kernel information on almost all systems today. I was inspired to form something like Acadia in the middle 1980s. There was another organization called CAMI. At that point in time, Carnegie Mellon Mechanical Engineering Department said that computer-aided design was not their bailiwick. It had no partial differential equations, and it was too graphics-oriented, and it didn't take the same kind of science that was required in traditional mechanical engineering. So I was elected to be the representative to CAMI for Carnegie Mellon University, and gave reports. So CAMI had about 70 international members, and their goal at the meetings was to capture the essential information of CAD-CAM and put it in a form that it could be used by different companies. And I list a subset of the companies that I remember being involved at the time. And at the same time, things were just getting started in 3D and in architecture and construction. And so it seemed to me that this would be an ideal organization to form, to put together an agenda that gave some leadership, not to the AutoCADs of the world, but rather to the users and industry, to have a strong, what we would call a user group, that would give advice and leadership to the AEC CAD area. Well, that never happened with Autodesk, being such a big player. So this agenda and the one about education and technology was never taken up. So that initial agenda failed, and I think, I think we're at a threshold where new initiatives similar to this user group idea, I think, would be very profitable. We have two platforms today that are open-ended, modern, not held up in a very strong proprietary sort of way, and that's Rhino and the Autodesk name. No, Dynamos. Thank you. You just blocked my mind. And I think both of these are interesting platforms. They're both open. They can be expanded on. And if the Acadia or other group wanted to get together and drive that to make it a full, rich environment, dealing with both untyped sketch level design work, and then evolving into structured BIM models. I think there's an opportunity to do that, and I kind of leave that as something that I would make as a proposal for Acadia. There's still serious work to be done at the systems level, that dealing with the object files. All of BIM talks about objects, right? Both positively and negatively. But in fact, the real unit of operation in BIM today is a file. We need to get rid of files, have an amorphous cloud-based representation of the model, and that we're able to structure, query that, and maintain the consistency of that over the user. So the second issue is the customer is synchronization. That means that the timestamp on every file should be later than the precedent dependent. You're tracking the dependency chains, so that if I make one change, I know all the things that were dependent upon that. And that's a huge amount of work, huge amount of errors. That is really a fantastic database task. And I think that's something that we'll see in the near future. Acadia, of course, does the best of that because they can propagate changes over multiple files. They have no file size limitation. That is, they're working on objects. In most cases, an object is multiple files, but they're not limited. So my comments here is I'm excited. I'm pleased to have had the opportunity to be leader of Acadia in its forming days, and I think there's still some. And it's exciting to see all the new work going on, particularly in design and fabrication. And I think there's some leadership and strategic objectives that also still need to be done, that I came in at the beginning to push for. Thank you very much.